The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Welcome on to this webinar about news in SCIA Engineer 21. Today, again about concrete and specifically about extensions in code-dependent deflection calculations. First, before we start, just quickly reminder that during the webinar you are muted, but please ask the questions into the dedicated panel, and we will try to answer as much as possible during the webinar. And maybe if some question will be really interesting for all of you, I will try to mention it at the end of this session. And mainly the webinar is recorded and will be posted on our YouTube channel. So if you miss something, you will be able to check it later. So my name is Tomáš Pajl. I'm product owner responsible for concrete domain in SCIA. And today I will be your presenter, and with me is here also Radim Matela, who will try to answer your questions as a moderator. Just a quick recap about what's new in concrete in general. Beside this code-dependent deflection area, where we finally are able to considering shrinkage during the calculation. Also, you will be able to manually input combination also for long-term deflection state or immediate deflection. And also we've provided the standard and detail output from this calculation, so it should be more transparent. There is another big part of, let me say, usability improvements. About that is already a webinar on YouTube, so you can check it. But I believe there is a lot of nice improvements which can improve your work. So quickly, I will summarize the extensions of code-dependent deflection calculation. Then we will go through some theory, and on simple example I will try to really go into deep using the detail and standard output. So I hope it will make clear what's going on background during the calculation. So about the shrinkage, just quickly about the motivation, it's clear that it's beside the cracking and creep, very important phenomenon which increase the final deflection. So we, for purpose of code-dependent deflection and calculation or manual input of shrinkage strain, we are able to transform this to curvature and then to the deflection of 1D or 2D members. It's also possible to visualize the results about the shrinkage graphically or in numerical output, so you can check it also in this way. About manual input of combination, until now it was just possible to use automatic combination generation. So based on your total combination for short-term effects, the necessary combinations for long-term or immediate state were derived somehow, and you missed the functionality that you would like to somehow influence this automatic generation. So we simply enable to input your preferred combination for creep and immediate deflection as a non-linear linear state, and this linear state is used for each total combination from envelope, I mean linear components. So again, I will explain it later what is it behind. And finally, codependent deflection with standard and detail output. Again, based on your feedback and requests, we introduced this, so you should be able to check what combinations are used during the calculation, what internal forces, about material properties, long-term, short-term, about stresses of uncracked and cracked cross-section, and finally the stiffnesses. It's part related to the calculation semi-results, and then we present also the deflection itself. And in detail output, you even find more details how it's really calculated. Okay, so it's quick summary. Now, what I will use as an example, it's some simple slab modeled as a 1D or 2D approach with some user reinforcement in on the bottom surface. So there is some assumptions about material and about the reinforcement, and mainly we assume 4 load cases, 2 permanent load cases for self-weight and dead load, and 2 variable load cases, one short-term from category B and another one representing, for instance, wall partition, which is a long-term effect assumed in category E. So from these categories, load groups, the psi factors are then derived. Okay. Quickly, I start with some theory, and then I will skip between this presentation and SCIA Engineer. But first, quick summary why we need to limit the deflection. According to the code, in part of service limit state, we have mentioned in chapter 7.4, there is necessity to check the deflection first to avoid bad appearance, where the long-term deflection should not exceed the limit of 250 of length or span. And there is also another limitation to avoid failures of adjacent parts after the structure is built. And in this case, the limit is 500 of the span ratio. Even there can be another limitation, like for instance, if we have flat roof and with significant excessive deflection, then if the water is keeping there, it's necessary, it's additional load, which even can cause the failure of the structure. So even the deflection control can be important for ultimate limit state. But never mind. Now, how is the deflection calculated in SCIA Engineer? And codependent deflection actually is a semi-nonlinear method where first step is to calculate linear analysis of the model, and based on these results of internal forces, it's necessary first to check if the section is cracked or uncracked. So actually we check the short-term stiffness, where we use the elastic modulus, but with possibility of cracking. So we can see that due to the cracking, the stiffness can be reduced. And then we have also long-term effect for creep and for shrinkage, or described as a creep or shrinkage. It's rheological phenomenon where it's covered actually by effective modulus, which is reduced by the creep factor or creep coefficient, and related to the shrinkage, we have some assumptions about the shrinkage strain. Basically, we need to check this total deflection and additional deflection, and to be able to calculate those two values, we actually need to calculate 5 states. So first, we need to calculate the short term deflection, which is calculated on some assumed load level, we call it total. Then we have long-term effects, the creep, where we need to calculate actually the creep for long-term cross-section, including the cracks, and with effective modulus of elasticity. And also we need to calculate the short-term creep deflection, because the difference between those two actually is the increment of the deflection caused by the creep. Yeah? So that's the reason why we need to calculate this load combination twice, with short-term stiffness and long-term stiffness on the level of creep. For this same level, we are also calculating the shrinkage itself, which basically is independent on the load, but it's important that the whole CDD calculation is based on the stiffnesses, so we need to somehow derive the stiffnesses from the curvature, and for this we need some loading level. Yeah, so from this perspective, it's assigned to the long-term effects described as a creep combination. And then we need to calculate the immediate deflection, which is the deflection which is then necessary for calculation of additional deflection. So according to the total deflection, if we from that put the additional deflection, we actually, or if from the total deflection we remove the immediate part with permanent load and some long-term variable load, then we have this additional deflection and we can check the limit. Yeah. Now it's important to understand what load combinations are used, and basically we have now two ways how the load combinations are used. First is automated way, where you input the total combination, which can be envelope, frequent, or quasi, or whatever you want. So it means this load level, yeah. And then from this envelope combination, we split it to the linear combinations, for instance, total 1, total 2. And from this total combination linear is derived the necessary combination for creep using the psi factors for variable components, or immediate and immediate combination, where is removed the short-term and medium variable load. Yeah? And we do it for first linear combination, second linear combination, and so on. Yeah? So for actually the envelope combination, we have some load sets, and each load set actually means one state of the deflection. Yeah? So finally, we have, for instance, if this total combination and creep and immediate deflection are really different, then we have five different stiffnesses. So it means short-term creep, long-term shrinkage, and immediate deflection. It means calculation 5 FEM analysis per this load set. And if we have quite a lot envelope combination, then that's the reason why it takes such a long time. Yeah. Okay. Then we have another approach which I will describe later in detail, and this is manual way how you can define the combination. So it means, again, for total, as always, you input some frequent, quasi, whatever you want, and then for creep and immediate deflection, you can input also your user-defined combination. Now it can be just linear combination, and this linear combination is used always for each load set. So it means for each linear combination of total is used the same combination for creep and same combination for immediate deflection. Yeah. So it's the difference because actually for this load level creep and immediate deflection, you assume the same load level for all linear combination of total envelope. Yeah. Then here is also another very important part, which is the characteristic combinations, because you saw it also here in automated way, because actually to decide whether a cross-section is cracked or uncracked, we actually need, beside this combination for deflections, we need also the characteristic components, characteristic combination. And again, it means for each combination in this load set. So it means for total, creep, or immediate. And if we have the manual input of the combination, we have again characteristic combination for this linear total combination. But in case of manual input of creep and immediate combination, we assume that the characteristic combination for this load level is actually the same. So it's again some kind of simplification, which we will see later. Okay, so now maybe it's time to go to the SCIA Engineer. So here is this example of slab modeled as 1D or 2D. If we want to calculate codependent deflection, we need calculated linear analysis, and we can go to the codependent deflection and play with the properties of the command. So you can see now I am in the mode that I have activated automatic generation of the combination. As input, I'm using the frequent envelope combination. As a type of reinforcement, I'm using the user, but it's one of benefits of codependent deflection. You can also use required reinforcement or provided. So actually you can save the time to input your reinforcement manually. But for now, we will use the user reinforcement. And actually this is all what we need to start the calculation. But before that, let me just first check our limits of the deflection. So here in the code-based settings, we can see that for deflection control, we can set the limits for 1D as the ratios of the span, while for 2D we are now limiting to input absolute values. So actually, if I have the length of the slab or span of the slab for meters 0.2, I can calculate directly here the limit. Sorry. In the settings, so I will just put, and it's in millimeters. So once more. So actually this is my limit for total deflection for 2D, and for additional deflection we have the limit. Then it's good to check what tensile strength of the concrete is used to check whether the section is cracked or uncracked. About using effective modules, it's not necessary to consider now, because codependent deflection handle this automatically, so you cannot influence it. And for now, it's all. And mainly for now, we will not consider the shrinkage. So it's now off, and we use the user value of creep coefficient, which is value 2.0. Okay. So now I will go and calculate the 1D and 2D model, and you can see the results are already calculated. So we can immediately go into the detail of the calculation. So I will now explain using this standard output, for instance, what's going on background. So first, we can see that we have some assumptions about the cross-section. So here is this reinforcement. We have here the creep coefficient and the shrinkage. Now what is important that here you can see these load states. So we have load state for immediate deflection, we have state for the creep, and we have load state for the total deflection. You can see that we have acting load and internal forces, and we have characteristic load with different load set, because if we compare, for instance, the combination key for this immediate load level, you can see that actually this load case LC4, which is variable load case, is multiplied by the psi factor 2, so 0.8, while in characteristic combination the C2 factor is not used, but actually is used C0 factor for non-leading variable loads, and this is leading variable load, so it's without any coefficient. Yeah, so you can check what combinations are used for each load level and what internal forces. Okay, then what is here mentioned is the material properties. You can see that if we have short-term case, like immediate, total, or creep short, we have elastic modulus, while for the long-term stiffness, we use the effective value, which is calculated using the creep factor. Then there is part related to the stresses. So first, we need for each load level, we need to calculate the stiffness, and for calculation of the stiffness, we need first to know if the section is cracked or uncracked. So maybe it's time to switch back to the presentation, because here is explained how it's calculated again in CDD. So we have actually the stiffness and the load, and actually for calculation of the stiffness, we interpolate between phase 1, where the section is uncracked, and phase 3, where the cross-section is fully cracked. To understand where we are actually, and this is checked using this characteristic combination, we need this load level of characteristic combination, and we can compare this load level with some critical loading on the level of initiation of the crack. Yeah. So how, for instance, we can calculate this critical moment? It's very easy that for the tensile fibers of the concrete, we said that in these fibers is this limit of tensile strength of the concrete. So it's some critical stress in the concrete. And if for the characteristic combination on the idle cross-section without cracks, this value of cross-section in concrete is higher, then it means that the cross-section is cracked. If it's opposite, then it's uncracked. Yeah. If the cross-section is cracked, then we need to calculate the stress in the reinforcement, in tensile reinforcement, and this stress is then compared with stress again of the cross-section in the stage of crack initiation. And by these stresses, actually, we can calculate the distribution factor, and with this distribution factor, we can interpolate the stiffness for this load level as some interpolation between state of uncracked stiffness and cracked stiffness. Okay, so now if I go back to the SCIA Engineer, you can see here is the stress in the concrete. Here you can see the limit value, which is same for all loads and load levels. Yeah, and for each characteristic combination, actually the value is calculated and compared. Yeah, so you can see that for all these loads, this limit is achieved. So actually it means that each section is cracked. Yeah. Now how you can check, for instance, how this stress is calculated. Yeah. So I can choose, for instance, this level of creep short term. Here we have this moment, which is given by the combination creep, and this creep combination for the characteristic components is given by this combination key. Okay, and the stress for that should be 3.14. Okay, so now what I can do is, for instance, to go to the SLS reinforcement check, and for this combination which is already prepared, maybe I will just show you it's really prepared in this way, so we can see that all load cases are there with multiplication factor 1. Yeah? And I can, for instance, use the section check, select the extreme cross section, which is section 7. Yeah? And here I can see that I have this combination, which is also in the CDD with the load level 21.6 moment. And I can check actually the distribution of the stresses. Yeah? So here I can see the limit value of the tensile concrete stress for uncracked cross section. Yeah? And same I can then check because I can see that the uncracked state says that actually my cross section is cracked. So then I can go and calculate for the same load level again the stress distribution, but now I am assuming that the cross section is cracked, so you can see that concrete is not working in tension, and I can calculate the stress in the reinforcement, which is 296. Yeah? Okay, so now if I go back to the preview of the codependent deflection, I can check both values. Yeah? Sorry, it wasn't necessary to recalculate, but never mind. So here I can see this 3.14, and here I have this 296, which is again compared with the stress in the reinforcement for the load level where the cracks are just initiating. Okay. Now you can see that for long-term state, actually I have different low level in concrete and different low level in steel. Why is that? It's the reason we have different elastic modulus, which now is using the effective part, including the creep. And again, we can check the stress. So just quickly, what you have to do now is just go to the concrete, and for calculation, you need to activate this effective modulus of concrete. And again, then the procedure can be same. So I will just activate the command. Again, use the section check. And now you can see I'm using the effective modulus, same combination at same load level. Yeah. And I will check just the stresses. So for concrete in tension, 2.95 and 307. Yeah. Okay. So back to CDD. Display the preview. And now it's recalculated because I changed the settings in setup, which actually is not influencing the CDD, but it's consequent that each change in setup means deleting of the results, but never mind, the result should be calculated fast. Okay, so we are back, and here you can see this 2.95 and 307 or 8. Okay, and then based on the stresses, you can see the distribution factor and calculated the stiffnesses. Okay. If you need more informations, like the detailed one, where, for instance, you are looking for instance, cracking forces, etc., you can display the detail output and get more results, like what reinforcement specifically is with the position, and each state, like here, for instance, immediate deflection, is then elaborated in detail. So you can see again the forces, but also the cross-section characteristics for cracked, uncracked, and linear cross-section. Then you can see the cracking forces and same results as we described already, and the stiffness calculations in detail. So you can see also the stiffness, for instance, axial for uncracked state and fully cracked state, and then the interpolation and for each state. And as the last part of the output, you can see also how the deflection is calculated. So for instance, here you can see the creep is really calculated as a difference between short and long state. You can check also what stiffnesses actually are sent into the solver. So for instance, you know from property modifiers that we have ability to change or modify the stiffnesses. So actually you can check in same way what is sent to the FEM analysis. And the same approach is actually also for the 2D. Yeah, so for the 2D, we have actually the internal forces, again the combinations, but here there is difference that you need to calculate the stiffnesses for both directions of principal stresses. Yeah? So here is direction 1 with same content, but immediately we have also the direction 2. So for instance, now we have cracked section in the main direction because the slab is one way, yeah. So it's obvious, but for the opposite direction, it's absolutely clear that the section is uncracked, yeah, because it's one-way slab. So if now I'm going to the standard output and I will check the output for 2D, you will see it in better way how it looks like for 2D. Yeah. So here we have 1D, and for 2D, again we have load levels. Yeah. And for each load level, actually we have direction 1 of principal stress and direction 2, and actually the calculation is same. Yeah. So here you can see that if the cross section is uncracked, the stiffnesses of the idle cross section not cracked is used, and actually the stresses of cracked section is not calculated. Yeah. Now how it's changed when I'm using the manual combination. Yeah. So for instance, if I disable the automatic combination, I switch off the teams, sorry about that. Okay. So if I disable the automatic generation of the combination, you can see that I have again possibility to select the same combination as previous, the frequent one, but for the creep deflection, I can use for instance, some linear combination SLS quasi user, and for immediate combination, this SLS immediate user. We can check the content of the combination, where, for instance, the immediate, you can see that now I have only the permanent loads. So this long-term variable load LC3 I'm neglecting as my input. Yeah? And for instance, SLS quasi user, you can see I'm a little bit playing with the creep, the combination factors Psi2 but according to my wish. Yeah? And again, I can recalculate the results with these settings. Yeah? And check again in the output if I understand what's going on background. Yeah? Okay. So you can see the unity check has changed because I have different load level. If I display the standard output again, we will explain what's different here. So here you can see again the load levels for creep, for immediate, and for total deflection. And now you can see that for immediate deflection and for creep deflection, we have actually assumed the same internal forces for acting load and for the characteristic part. So is this simplification? While for the total combination and, for instance, in this case, linear combination from the envelope, you can still see that there is difference between acting load and characteristic load. Yeah, you can see also the combination keys, which actually follows what I showed you in the SCIA Engineer and the dialog for the definition of the combination. Yeah. What's important to mention that, for instance, for the creep combination, you are able to influence actually the combination in terms of instead of using psi2 factor, use some user input value, but in case of manual combination, it will not influence the combination at all. So it means really what you input for creep and for immediate deflection as a linear combination, this will be used for each load set. So it means for each combination derived from the total envelope. Okay. And here, for instance, you can see that before for automatic generation combination, we have all sections for all load sets actually with correct section in the middle of the beam. But here you can see I changed the load level. So now my tensile strength of concrete is below the limit. So actually I have incorrect section in this case. Okay. Now what I will do is actually focus on the shrinkage because it's also new. So until now we assumed that shrinkage is not considered. If you want to calculate the shrinkage, as the default is selected the automatic way how the shrinkage strain is calculated using the humidity level and also the date where the shrinkage starts and also when the shrinkage ends, which is same also for the creep. Or you can choose your user input value. So for instance, in our case, we will use this 5 per mil. Yeah? And with that, we can go into the calculation. Yeah? So nothing complicated. I'm using again my, for instance, manual combination input, doesn't matter. And we will check how the results looks like. So again, I need to calculate all the states of load with nonlinear stiffnesses. And we have the results. Now you can see that it's increased quite significantly. If we now go to the brief table, you can see that actually we extended the output for this shrinkage deflection caused by shrinkage strain and derived curvature. and same is for 1D as well. Yeah? So it means that you can select this value also in the result as a result, and you can display the results also graphically. Yeah. So for instance, if I will now also display results for 2D, we can see also the distribution. Yeah. If I go now to the detail output or standard output, doesn't matter. First, I will start with standard output. You will see the change. So now I do not have 4 load levels actually, but I have also another level for the shrinkage. Yeah. As I said, it's independent on the load, but to be able to calculate the stiffnesses, we actually need some load level. Yeah. So actually, then we send this stiffnesses with this same load level as is assumed for this shrinkage, but you can see there is difference between, for instance, the creep and the shrinkage for the same loading. Yeah? And the reason is because the stiffnesses are influenced by the curvature from the shrinkage. Yeah? So to understand it even more, we can go to the detail output and explore how the curvatures from the shrinkage strain are calculated, and how even the same approach like for other load sets are used. So you need to check if the section is cracked, uncracked, and then calculate the stiffness by the interpolation. So here we have shrinkage deflection. It's considered as long-term stiffness, so we're using the effective modulus of elasticity. And beside the stiffness calculation, you can see also that there is calculated the strain and curvature calculation caused by the shrinkage. Okay. And basically that's in a nutshell all what I wanted to mention today. So I will ask Radim if there is some question which is interesting for all the audience.
No, there is not anything.
Okay. So thank you for your attention. Maybe before we end this session, I would like to mention one maybe important info, that also it's very important how you will discretize your 1D members, because you can choose that you want one mesh element per the member. So it means actually that you will calculate the stiffness just once for each load set, and it means that this stiffness is used for the whole beam. The code enables this approach, but actually the reality is different, that of course where I have not loaded the member significantly, or the internal forces are not high, definitely we have full stiffness of uncracked section, while for the extreme of internal forces we have the cracked stiffnesses. Yeah? And to achieve this distribution of the stiffnesses, we need to split the member to more mesh element. So as a default for CDD is assumed at least 5 mesh elements per beam. If it's below this value, then there is message that you should increase this value, but still you can ignore this message and you can calculate, for instance, with just one mesh element, but with this consequence that you will assume this extreme cracked section for a whole beam. Yeah? So definitely you will get bigger deflections than the reality. Okay, so that's all for today's session. If you have any questions later, don't hesitate to contact me, and I hope you have enjoyed this topic same as me. Okay, bye for now.